Okay, so we're going to try something a little bit different for the start of stoichiometry. Since I'm not here, I'm going to go ahead and make a video for you, and I want you to watch the whole video, even if parts of it don't make sense. I think this will help you to have at least a baseline of what we're doing when I get back. If you need to watch this multiple times within the class period, that might be helpful. I tried to do some color coding to make this a little bit easier, but go ahead and watch this video and then try the first homework assignment or the first problem on the back of your homework assignment, just to give that a shot and see how it goes. So here we go. This first slide is review, and it talks about ratios. So we had this reaction up on the board last time, and we said if 2 molecules of silver nitrate react with 1 molecule of barium chloride, how many molecules of each product will be produced? And you all correctly said that we'd get 2 molecules of silver chloride and 1 molecule of barium nitrate because the ratios are 2 to 2, 1 to 2. You found those ratios in there. For every 2 moles of silver nitrate we put in, we'll get 2 moles of silver chloride. If 2 moles of silver nitrate react with 1 mole of barium chloride, how many moles of each product will be produced? Well, we'll get 2 moles of silver chloride and 1 mole of barium nitrate. Again, those ratios stay the same. It's just like in our recipe for the banana split last time. If we had the right number of scoops of ice cream, we were going to get a banana split out, or 2 banana splits out, or 3 banana splits out. If we double it, if we have 4 moles of silver nitrate and 2 moles of barium chloride, well, we'll get 4 moles of silver chloride and 2 moles of barium nitrate out. Our ratios stay the same even if we have larger quantities. And then the last one, if we have 1 mole of silver nitrate with half a mole of barium chloride, well, we're going to get 1 mole of silver chloride and half a mole of barium nitrate. That's just to get you used to those mole ratios and how those things work together. Using moles here really could be thought of interchangeably as molecules. It's just that it's a much larger number. You're going to see some writing on the screen here, and then we're going to move forward a little bit. So as we move forward, we're going to add masses to this, and there's going to be some writing on the screen that I want you to watch fairly closely, and then I'll talk about what the writing is once we get there. So here I'm doing a little bit of a mass conversion, and whoops, sorry, I'm going to pause it right there. So the first question here says, if 15.5 grams of silver nitrate react, how many moles of silver nitrate are reacting? So this is just asking you to figure out how many moles are in 15.5 grams. I'm going to walk you through this problem step by step to get you to the end product. So the reaction is up at the top there in bold, and this first part is going to be in black. So at the top you see 15.5 grams of silver nitrate, and then I went to the periodic table and found the molar mass of silver nitrate, and when I added all those up, I got 169.88 grams. So I set it up like that. We've got grams on top on the left, so we need grams on the bottom so that that'll cancel. And when you divide that, you should get 0.0912 moles of silver nitrate. That's the answer to that first bullet point. All we want to do there is go from grams to moles. We have 0.0912 moles of silver nitrate. So here's the next piece. How many moles of barium nitrate will be produced? We're going to do a mole conversion here, and you can see what that looks like in the purple. So 0.0912 moles of silver nitrate, we just take what we had from the last piece, and then our mole ratio is 1 mole of barium nitrate for every 2 moles of silver nitrate. I got those straight out of the balanced equation. You can see that there's 1 mole of barium nitrate in the equation, and there's 2 moles of silver nitrate in the equation. That's where I got the numbers there. So what that's telling me is for every 2 moles of silver nitrate I put in, I should get 1 mole of barium nitrate out, or I'll always get half as many moles of barium nitrate out as I put moles of silver nitrate in. So we're going to just divide by 2 here. That's all the math that it takes. So 0.0912 divided by 2 gives me 0.0456. You'll see also that our units cancel, and we're left with moles of barium nitrate. On to the next piece. In the green here, you're seeing 0.0456 moles of barium nitrate, and we're now going to grams of barium nitrate. This is the last step in most of these problems. So I have moles of barium nitrate, the moles of the product that I'm looking for. Now what I need is how many grams of that is there. So really, if I wanted to find out how much I produced, I would want to know how much in grams I got. So I went to the periodic table, added up the molar masses of barium and nitrogen and oxygen, in the right quantities, and I got a molar mass of 261.35 grams. So again, we put the things in the right place. We've got moles on top, moles on bottom, so our units will cancel. And when we multiply those two things together, we'll get 11.92 grams of barium nitrate. So to walk through that whole thing again, this is a three-step problem. We started with a mass of silver nitrate, 15.5 grams. We found out how many moles that was, then went from moles of silver nitrate to moles of barium nitrate, and then went from moles of barium nitrate to grams of barium nitrate. There's no way that you could do this grams to grams in one step. You have to do it in three steps because, as that kind of sub-point says there, we have to use moles to convert from one chemical to the other. That's the only way we can go from one chemical to another within an equation, and then we can find the number of grams. I'll let this play again, and the last bullet point there asks you to do a second part of this problem. So now it's asking how many grams of silver chloride will precipitate out of the solution, assuming that we have the original 15.5 grams of silver nitrate. So this is a two-part problem. We can assume that 15.5 grams is always going to be 0.0912 moles of silver nitrate. So I skipped that piece and did the mole ratio, and it's a 2-to-2 ratio now. Now we're going to silver chloride, and if you look at the balanced equation, there are 2 moles of silver chloride in that balanced equation. So on top I put 2 moles of silver chloride, and on bottom I put 2 moles of silver nitrate to cancel my units. I ran the calculation, and when I multiply by 2 and divide by 2, I should still get 0.0912 moles of silver chloride. So that was my answer. After that, I did the step that's in the green above, and I added up silver and chlorine to find the molar mass, and then multiplied by that molar mass to find out how many grams of silver chloride that is. So I did the same thing as I did up above. The step that's purple up above was the first step in blue. I did the 2-to-2 mole ratio, and then I found the molar mass and multiplied by the molar mass to get 13.1 grams of silver chloride. So again, a three-step problem. I just kind of skipped that first step because it was going to be exactly the same as it was in black for you up above. Okay, moving on to the next piece. So this is a new reaction, and you can see it again in bold, and we want to know how much aluminum oxide is formed from 3.4 grams of aluminum. So in the red, you'll see the very first step. This is what was in black before. I started with 3.4 grams of aluminum, found the molar mass of aluminum, and divided by that. Again, our units are set up so that units cancel. We're left with moles, and you should get 0.126 moles of aluminum in 3.4 grams of aluminum. The next piece here is in black, and that's going to be our mole ratio. So for every 2 moles of aluminum we put in, we should get 1 mole of aluminum oxide out. And if you look at your balanced equation, that's true, and the numbers in your mole ratio should show that. For every 2 moles of aluminum we put in, 2 moles of Al on the bottom, we should get 1 mole of aluminum oxide out, so 1 mole of Al2O3 on the top. What that means is we're going to divide by 2, so 0.126 divided by 2 is going to give me 0.063 moles of aluminum oxide. So that's that second step in black. The third step then is to go to grams. So most of these questions are going to be 3-step questions. We want to know how much aluminum oxide is formed from 3.4 grams of aluminum. We found the moles, we did the mole ratio, and now we're going to go back to grams just like we did on the last slide. So that 0.063 moles of aluminum oxide, I found the molar mass of aluminum oxide, 2 aluminums plus 3 oxygens, is 101.96 grams. And then we multiply those two things together. Again, our moles are opposite, so those are going to cancel out. We're going to multiply by the 101.96 grams, and that should give us 6.42 grams of aluminum oxide. So one more time, a 3-step problem. We have to start by finding the number of moles, so 3.4 divided by 26.98. Then we do a mole ratio, so times 1 divided by 2 was our mole ratio there, and then we go back to grams. I highly, highly, highly recommend that you write this stuff out this way because as you can see, there's a lot of numbers and a lot of stuff to keep track of here. Okay, so the next one I want you to try, it will look exactly the same as the one that we just did, except that instead of solving for aluminum oxide, you're going to solve for iron. So the red step will be exactly the same. In the black, you're going to substitute 2 moles of iron for your 1 mole of aluminum oxide. And then your molar mass will obviously be different because you're searching for iron, not for aluminum oxide. But you go ahead and try that. I'm going to pause the video just for a second, and then I'll show you how to do the last piece. Okay, you may need to pause it for a little bit to finish that up, but I want you to try that before we move on here. So the last piece here is in black, and I did this in steps as well, but this asks how many grams of iron 3 oxide are needed to react with the 3.4 grams of aluminum. So this asks it a little bit differently, but really we're solving for a similar thing. Just because it's another reactant doesn't mean that we have to solve this any differently. Again, 3.4 grams of aluminum is going to have is going to be the same as 1.26 moles. So I started with 1.26 moles of aluminum. My mole ratio really doesn't change even though we're looking at another reactant. So my 2 moles of aluminum is on the bottom because that's what's in the balanced equation, and 1 mole of iron 2 oxide is on top because that's what's in the balanced equation. It doesn't matter that that's another reactant. So my mole ratio says that I need to divide by 2, and if I look at my balanced equation, that makes sense. For every 2 moles of aluminum I put in, I need only 1 mole of iron oxide. I don't need 2 moles, I don't need 3 moles, I need 1 mole of iron oxide for every 2 moles of aluminum that I put in. So we'll divide by 2 here and get 0.063 moles of iron 3 oxide. The next piece then is to go back to grams. So we've got that 0.063 moles of iron 3 oxide, and you're going to look at the periodic table, add up 2 irons and 3 oxygens, and you should get 159.7 grams per mole. When we put that in the T-chart, we should have moles on the bottom. Again, we want those units to cancel. And then we'll have grams on the top, which means that we're going to multiply, and we should get 10.1 grams of iron 3 oxide. Now, there's a lot of stuff there, and we worked through a whole bunch of problems super fast. What I would really recommend you doing is going back through, making sure that you've got this written down, and that you're writing it really pretty similarly to the way that I am. There's some really, really strong patterns here that if you look back through these, you should be able to pick up. Almost all of these are solved in a very, very similar way. If you try to do this in your head, it will be a major, major struggle for most of you, just because there's so many numbers and so much stuff to keep straight. If you pick up the patterns, though, and are willing to write this down, this can really be picked up and just patterned in your mind. It doesn't take a lot of even really a deep understanding to be decent at this if you can pick up the patterns and figure out where to put things. So take a little bit of time as you go through class here and make sure that you've got these problems pretty solid in your mind, and then also go through at least the first question or two on the homework assignment. I'll grade the first question and make sure that you can understand that. If you need to work together, that's perfectly fine, but get each other to a place where you can kind of have an idea of what we're doing before I get back on Friday. I hope this helps. If you have questions, feel free to email or text me. I might be able to get back to you, but I might not, so you may have to fend for yourselves a little bit. Good luck.